Imagine you are organizing a messy bookshelf. You move books around, group similar ones, and arrange them neatly. Gaussian elimination works the same way. It systematically simplifies equations, making them easier to solve. Welcome back to our Introduction to Linear Algebra series. In this lesson, we will learn Gaussian elimination, a fundamental technique for solving systems of linear equations. Gaussian elimination helps us transform a system into a simpler form so that we can quickly find solutions. Now, what is a Gaussian elimination? Gaussian elimination is a method that systematically reduces a system of equations into a simpler one using three key row operations. What are they? First of all, we have to we have to understand the basic of it, right? So, for example, if we have a very simple system like x plus y, if we have a system called 2x plus y equals to 3, this is the equation, right? Not a system, this is the equation. This equation, if we know that we can multiply both sides by a constant, right? For example, if we multiply both sides by 3, then we will get what? 6x plus 3y equals 9. So this equation is equivalent to this equation, right? We have this equivalent sign, so both of these equations have the same solution, and like these are equivalent, so nothing changes here, right? We can do this. We can multiply the whole thing, left side and right side, by constant, which is in this case 3. Okay, got it, right? Then we can also do another thing, that is, if we have another equation. For example, if we have 3x plus 3x plus, let's say, 2y equals 5. So in this case we have two equations. What do we know from substitution? Or we know how to do substitution, we know how to do elimination. So we could, like, if this is equation 1 and this is equation 2, we could add them both, right? If we add equation 1 and equation 2, what does it tell? So in that case we would add this and this, add this and this, the variables and the coefficients and the constants, right? So in that case that would be 5x, 3 plus 2 is 5x, and 2 plus 1 is 1y. So 2 plus 1 is 2y, sorry, 3y, and then 5 plus 3 is 8. What did we actually what did we do? We just added the coefficients, right? And then we got as a newer coefficient and also the constant. So we can also do this, right? Then we can also if we say that this is not equation 1, this is equation 2, and this is equation 1. We want to remove this 2x plus y equal to 3. So if we remove this and write it under the first one, 2x plus y equal to 3, does it make any difference? No, because this is the same. Like if we operate the same operations, if we apply the same operations, like multiply the whole thing with a constant and then add them, subtract them, we could do this, right? We can name this equation 2. This does not make any difference if we say this is 1 or this is 2. These are same, right? So basically we can swap these equations to to our conveniences, right? So if we understood these basic stuff, then we can set a we can define the three co-operations, three row operations, key row operations that we will be using to operate Gauss elimination. Okay, so we know that we can express this system with the augmented matrix, right? Let's say this is an augmented matrix. So we can write 2, 1, minus 1, 8. We are just replacing the constant and the coefficients. Okay, then minus 3, minus 1, 2, and minus 11, and then we have minus 2, y, 2, and minus 3. So this is the augmented matrix that we need to operate Gauss elimination. Okay, so this is not y, this should be 1. Okay, so what we can do is we can swap any rows. If we write this row here, and if we just swap this, both of these rows like this, like minus 3, 1, minus 1, 8, and then if we write 2, minus 1, 2, minus 11, and then minus 2, 1, 2, minus 3. these both of these systems will be equivalent. Why? Because we know that we saw earlier that if we like this whole row, this one row is an equation, and this row is an equation. If we write them like swap them and write them like this, nothing changes, right? We can do this. Basically, we can do this. We can do this row operation. This is called a row operation, swapping to any two rows. We can swap this with this, this with this, and this. We can swap anything with like any row with another. Okay, this is one operation. Then also, what we can do is we can basically multiply a row by a constant. Okay, scale an equation to make equations easier, like calculations easier. We can basically multiply any of this row with a constant. For example, if we multiply this row with a constant which is 3, then this will be what? This will be 6, 3 minus 3, 3 is 24. Okay, minus 3, 24. So this can also be done, because we know that if we multiply an equation, this row represents an equation, right? If we multiply a whole equation with a constant, nothing changes. So we can also do this row operation. We can basically multiply any row by a constant. Okay, then also we can subtract or add rows. For example, if we add row 1 and row 2, and then that addition, like that result, we can replace that result with any of these. For example, if we add row 1 and row 2 like this, if we add row 1 and row 2, and we will get row 1 prime, right? So in that case, that will be minus 1. This 2 and minus 3 2 and minus 3 will be added, and that will be minus 1. So let's put minus 1. We are replacing the result in row 1. Okay, not row 2. So we can do either. Okay, so if we add this, it will be 0, and then if we add this 1, add this, it will be minus 3, and the rest will be the same. Okay, so we can also apply this kind of operation, row operation, in a linear system. This is called add or subtract rows. Okay, so how these becomes the same. Why? Because we know that we can add or subtract any two equations, and if we after adding, what we get is actually equivalent to the first one or the second one. Okay, we can easily say that. Okay, so this is what the 3 key row operations that we will be using to operate Gauss elimination. Okay, then let's get introduced with 2 of the forms that we will be targeting to achieve. One is reduced row echelon form, and another is just row echelon form, not reduced. Okay, so by applying Gauss elimination, all we want to do is to make our linear system look like this. Okay, so actually, what is a row echelon form and what is a reduced row echelon form? Let's understand those first. So first of all, if a row does not consist of entirely 0, what does that mean? Which like this, if a row does not look like this, all entries are 0. Okay, that means if a row does not consist entirely of zeros, then the first non-zero number in the row is a 1. Like to achieve this row echelon form, we have to have these 4 properties. Okay, so if a row does not consist entirely of zeros, then the first non-zero number in the row will be a 1. In that case, look, the first non-zero number in the row, which is like not consist of entirely of 0, in that case that will be different case. So if a row does not consist entirely of zeros, then the first non-zero number, this one, which will be a 1. Okay, in a row echelon form, we call this a leading one. Okay, if there are any rows that consist entirely of zeros like these, then they are grouped together at the bottom of the matrix. If there are any rows that consist entirely of zeros, then we have to group them at the bottom of the matrix. Okay, in a row echelon form or a reduced row echelon form. Nice. Next, in any 2 successive rows that do not consist entirely of zeros, the leading one in the lower row occurs farther to the right than the leading one in the higher row, which means this row has a leading one, which is this one, and then the lower row has also a leading one, which is this one. But the leading one of the lower row will be farther right than the higher row. Okay, leading one of the higher row. So this will look like 1 1 1. So this one cannot be here, and this one cannot be further left there. So that will be always further right. The down we move, the further right the leading ones will move. This is not necessarily mandatory that we will have to have this one after for example like this. So in this case we have a row that leading one is this one, and we have another row the leading one is this one. So we did not have anything here, right? So this is not mandatory that we have to have a one here and we have to call a leading one and this one a leading one, right? This is not mandatory. We may not have this kind of pattern. In that case that is completely fine. Okay, so many people get confused that oh, we have done Gaussian elimination and we did not have like this, we have a 0 here, so what to do. So don't need to get worried about that, because this is a leading one and this one is further right than this one. That is what we need. This have to be right to this one. Okay, right than this one. So that is all we need. We don't have to be like make this pattern like this, make this fancy pattern. No, that's not the requirement. Okay, so next each column that contains a leading one has zeros everywhere else in that column. So this column here contains a leading one, so it must have zeros everywhere. This is a leading one, it does not have zeros everywhere. That's why this is not a reduced row echelon form. To gain reduced row echelon form, we have to have zeros everywhere of that column except that leading one. Okay, but in a row echelon form, not reduced, in that case we will have to have zeros under those leading ones, not above. We can have anything above. Okay, so if we look the reduced row echelon form examples, we will see that everything else in a column that has a leading one is 0. Okay, anything else, that any column that has a leading one, other values of that column is 0, right, in a reduced row echelon form. But in a row echelon form, if a column has a leading one, then the values under that leading one will be 0, not above. Okay, so this is what reduced row echelon form and reduced row echelon form and row echelon form is actually this is what it is. Okay, so we will get to this later. Next, let's say we have a system of linear equation that has like 1 2 3 4 5 variables, and this column is for the constant, right? So these are the coefficients of the variables. We have to solve this system, right? We will be solving this system with Gauss elimination. So let's do this step by step. Number one step, we have to locate the leftmost column that does not consist entirely of zeros. So what does this mean? If we have a column that consists of like all zeros, then we have to ignore that and we have to locate the one that does not consist entirely of zeros. In this case, we already have this, right? This column does not consist of entirely of zeros, right? So in that case, we will work with this column. Okay, nice. The next step is interchange the top row with another row if necessary to bring a non-zero entry to the top of the first column, found in step 1. So we found this column in the step 1, right? So we will work through this. Okay, then what we have to do is the interchange the top row with another row. That means that we have to interchange this row with this row. Why? Because we have to have a non-zero number here in the first column, in the first row and the first entry. Okay, the column we located, we have to have the first entry non-zero. Okay, so that's why if we have a 0 here, then we have to interchange. Otherwise, let's say we had 6 here. In that case, we did not have to interchange this and this because we already have a non-zero. Okay, if we have a 0, then we have to shift the 0 to the down and make the other one go up. Okay, nice. This is the step 2. Step 2 is like basically if we have a non-zero, if we have a 0 on the top of the column, then we have to make the 0. We have to bring the 0 down and make the non-zero equation, like non-zero row, this another row up. So this is what they did, right? The first and the second rows in the preceding matrix was interchanged or swapped, right? We can do this. This swapping is a row operation, right? Key row operation. Okay, we can do this. Then step 3, if the entry that is now at the top of the column found in step 1 is A, multiply the row the first row by 1 by a in order to introducing a leading one. So what we want to do is we have to make this first entry the leading one of this row, right? We have to make this the leading one of this row. If we had 0 here and we like want to make this leading one, we simply cannot do that. Why? Because we are going to divide it by like 2. This we are going to divide the whole row by 2. Thus we will get 1. So 2 by 2 will be 1, 4 by 2 will be 2, minus 10 by 2 will be 5, and then and so on, right? But if we had 0 here like this, for example, if we skip the step 2, if we want to proceed with this, then we cannot bring 1 here, because if we divide it by 2, then nothing happens. This remains 0. This does not become the leading one, right? We cannot divide it by 0. So 0 by 0 does not make any sense. So that's why we have to do the step 2, right? To ensure that we have a non-zero number on the top. Okay, next step 3, we have to divide it by or multiply it by 1 by a. If the first value is a, then we have to divide it by 1 by a. So multiply it by 1 by a. So we have 2, so we are multiplying it by 1 by 2, right? Okay, nice. Then if we multiply it by 1 by 2, then we'll get this thing. And then step 4 is add suitable multiples of the top row to the rows below, so that all entries below the leading one becomes 0. What does this mean? We have to make all the entries below the leading one 0. Why? Because in a row echelon form, all the entries below the leading one are zeros. So we have to make this 0. This is already 0, so we have to make this 0. How can we make this 0? What we have to do is we have to multiply the first row with -2 and then add to the third row. So -2 into first row, and that will be, so this is what we have to do. Let's write it. So multiply row 1 by 2 plus row 3, so -2 by 3, and then replace it in row 3 not. Okay, so row 3 prime. So this is what we have to do. So multiply it by the first row and then add these both 1 and 3, and then replace it in the third row, right? This like this. So after that, we have to now cover the top row. Like we are done with the top row. Okay, we have like secured this leading one and made all the bottom values of this leading one 0. So we are done with first row. Let's cover the first row and let's operate the same thing, the same method with the other rows. So now cover the top row in the matrix and begin again with step 1. Apply to the submatrix that remains. So we have to cover this whole thing. Like first row will be is done, right? So now we are working with these 2 rows. Continue this in this way until the matrix is in a row echelon form. So what we have to do, we have to start from the step 1. What was the step 1? We have to locate the leftmost column that does not consist entirely of zeros. So in this case, this is the column that does not consist entirely of 0. So we have other columns that consist entirely of zeros, but this one does not, right? We have to locate this. Okay, then we have to make this one 1, like before we make this value 1, the leading one. So like that, exactly same. We have to make this one 1, right? Make this -2 1. How can we do it? How can we do this? We have to multiply it by 1 by -2, right? This is how we can do this. So let's do this. The first row in the submatrix was multiplied by 1 by -2, -1 by 2 to introduce a leading one. So we are introducing another leading one like this. Okay. Remember that we are multiplying the whole row by 1 by -1. So other values will also change, right? Okay. The next step is not the next step. We are basically repeating the step 1 to 5. Okay. We are repeating this for these 2 rows. Okay. Then we have to make this 5 0, because the bottom values of the leading one will be 0. So in that case, we will have to multiply the second row with -5 and then add 2 and 3 rows. So -5 times the first row of the submatrix was added to the second row of the submatrix to introduce a 0 below the leading one. So this is what we have to do. Okay, so let's do this. If we do this, then 0 will be here and other values will also change. Okay, then we are done with this row also. We have got this leading one and the bottom values are 0. Then we have to cover the second row, and then locate the leftmost again. These are zeros. This is the leftmost, that is non-zero. So locate this and make this. We have to make this leading one. So to make this leading one, we have to multiply the third row by 2. Then this one becomes what? This becomes 1. This is the leading one, right? So this is what a row echelon form looks like. we have leading one, the other the below leading ones are the farther right than the first one, higher ones, and the values under the leading ones are 0. Okay, nice. So this is what we have to get. Then from this we can basically rewrite the like the equations that we like wrote. Like this is an augmented matrix, right? This was fetched from a system of equations. So we had 3 equations that look something like this. So we had a system of equations that looks minus 2x3, then this both of the first are 0, so we haven't write to x1 and x2 for the first one, right? This one is also 0 and this one is 7, so 7x5 equal to 12, and then the other equation was 2x1 4x2 minus 10x3 6x4 12x5 equal to 28, and the third one will also be consist of these values, right? So similarly we have to bring the equations back. So in this case most of these are zeros and ones. So let's do this. X1, so first one is 1, so x1 plus 2 x2 minus 5 x3 plus 3 x4 plus 6 x5 equal to 14, right? The first row is done. Then the second equation will be all 0, and then the third one is 1, so x3 0, and then fourth one will be minus 7 by 2 x5, the fifth one, and equal to minus 6. And then the third one is all 0, the last one will be 1, so x5 equal to 2. From this we can do back calculation and like determine the values of all variables x1, x2, x3, x5 and x4, right? We can do this. So we already know what x5 is, that is equal to 2. Then replace x5 here, then we'll get x3, then replace x3 here, right? So let's do this. X3 will be 5, so this will be 2, then 7 minus 7 and minus 7 plus 7, that will be 1. You can do all the like algebra in this. I will not be showing all. So if we basically replace x5 with 2, then we will get the value of x3 as 1. So we have a value of x3 and value of x5 already. So we have to determine 1, 2 and 4, right? So how to do those? So let's determine let's replace x3 and x5 in the first equation. In that case we will get x1 plus 2x2 minus 5, so 5 into 1, so minus 5, and then plus 3x4 plus 6 into 2 will be 12 and 14. So we still don't have the values for x1, x2 and x4, right? In that case what we will have to do is make the like set arbitrary values for x2 and x4. So let's say x2 is s, x4 is t. Okay, set some arbitrary value and then define according to that the value of x1. So in that case we will say x2 is s, so 2s plus 2s and then minus 5. Okay, so minus 5 plus 12 is plus 7, and then 3 into t, x4 is t, so 3 into t is 3t plus 3t equal to 0. Then x1's value will be minus 2s minus 3t minus 7. This is the value of x1. So the solution will be x1 we have the 4, the solution will be like this. X1 will be basically 2s minus 3t minus 7. Okay, what we did is we don't know the value of these. We have to set arbitrary values to x2 and x4, right? This s and t can be anything, any integer or any real number. So s and t belongs to the real set of numbers. Okay, so in that case if we have any value of st, then the solution will be x3 will be 1, x5 will be always 2, x2 will be always t. I mean, like we have to set value for x2 and x4, and x1 will be decided according to the value of s and t, the values we set. Like okay, so we have solved a linear system that has 5 variables: x1, x2, x3, x4 and x5, right? So this is how you solve a system with Gauss elimination. So I hope this was helpful. I know this is like somewhat tricky and like very exhausting trick, but this is how you have to solve larger systems. Okay, we cannot use substitution elimination anymore. So try solving these systems using Gaussian elimination. Like this is a 3 by 3, this is also 3 by 3. For practice, let's do this and drop your answers in the comment. See you for today, and we will basically in our next lesson we will dive into matrices and matrix operations, exploring how they make solving equations even more efficient. If you enjoyed this, don't forget to like, subscribe, and hit the bell icon. See you in the next time.